All right, we know the fundamental theorem of calculus, so what are some things you can do with it? Well, here's a question that is posed twice. It's not the same question, but it's a very similar question. Here you're given a position function, and you're asked to find the average velocity. And here you're given a velocity function, and you're asked to find the average velocity. So same question, different given information. So this first question is something that you could have answered perhaps maybe in Algebra 1. It was definitely something that we've seen in calculus, though. This average rate of change of a function, right? We know that the average velocity, remember that the velocity is the rate of change of the position. So the average velocity is the average rate of change of the position. Equals the change in position over the change in time. Okay, so that's going to be, in this particular case, x of 8 minus x of 1 divided by 8 minus 1. And pay attention to units here because x is measured in centimeters and t is measured in minutes. So this is going to make some sense because now we're going to get centimeters per minute as our units, which is a good unit for velocity. So we have 4 times 8 to the 1/3, or 2, plus 3 times 8. That's x of 8. And then we've got 4 times 1 to the 1/3, which is 1, plus 3 times 1. That's our position when x equals 1. And then our change in time is 7 seconds. No, minutes, 7 minutes. So anyway, we just evaluate this. This is 24 minus 7 over 7. And that will work out to be 17/7 centimeters per minute. So there's nothing really fancy about that. We're not really using any calculus here, really, because the average rate of change or the slope of a function from one point to another point is just a rise over run question. So now the question is, well, what if I didn't give you the position function, but I'm still interested in the average velocity? Well, the average velocity, guess what, is still equal to delta x over delta t, the change in position divided by the change in time. So if we could only find this position function, x of t. We don't have the position function, we have the velocity function. But wait a second, we know that the velocity function integrates to the position function because the position function differentiates to the velocity function. So we'll just take the antiderivative of this. So the t to the 2/3 is going to be a t to the, 2/3 plus 1 is 5/3, and then we'll divide by 5/3, which is multiplying by 3/5. So the 5's cancel out and we get a 3. Indeed, if you take the derivative of this, you'll get back to this, and then minus t squared. Now we have this plus c, right? So one thing we're going to notice, though, when we do our subtraction is that plus c is going to be in the first position, and our plus c is going to be in our second position. So we'll have a c minus the same c value. So we can actually forget about that c value. So we'll do the same process. We'll do x of 8 minus x of 1 divided by 8 minus 1. And this is the same idea, just different numbers. So we've got 3 times 8 to the 5/3 is 32. And 8 squared is 64. And then 3 times 1 to the 5/3 minus 1 squared over, once again, it's 7. And let's see, so this is 3 32s, this is 2 32s, so when you subtract you get 1 32. So 32 minus 2 is 30. Forgive me if I'm making any calculation errors, but the concepts are sound, I assure you. The velocity is measured, well, the position is measured in meters because our velocity was measured in meters per second, so this is meters on the top, and our time is measured in seconds, so we're back to meters per second again. All right, so one thing we just did here whether you realized it or not, is we evaluated a definite integral, right? Because the definite integral from a to b of the velocity function, is equal to the position function evaluated at b minus the position function evaluated at a. So this definite integral is actually something that we found, right? It's the numerator of this fraction. It's the definite integral of the velocity from t equals 1 to 8. That's what the change in position is, right? We've already talked about that. And now we're dividing it by 7, which is b minus a, so we can find the average rate of change, or the average velocity. So this doesn't have to be a velocity question. I'm giving you a function, and I'm asking for the average value of that function. And we just determined what that formula is. The average value of f of x on the interval a to b is equal to the integral from a to b of f of x dx divided by b minus a. And that's, I hope, an intuitive formula, because we just did it in this problem up here, and it kind of hopefully made some sense. So again, it doesn't have to be, f of x doesn't have to be a velocity function. I can say find the average of any function, and it's going to work out to be the same process. So here's a nice one. Find the average value of the sine of x on the interval 0 to 2. So I encourage you to pause the video and do it on your own, and then check your work. I'm going to go through this kind of quickly, though. The average value is going to be 0 to pi over 2 sine of x dx divided by pi over 2 minus 0. The antiderivative of sine is not cosine, right? Because cosine differentiates to negative sine, so make sure you put a negative there. And then we evaluate that at pi over 2. We evaluate that at 0. So that's negative cosine of pi over 2 minus negative cosine of 0. Well, that's 0 minus a negative 1, or 1, divided by pi over 2, so multiplying by 2 over pi. So the average value of the function is 2 over pi. Kind of a fun answer. So if we now look at that on a graph, this is the line y equals 2 over pi. It's around about 2/3, right? Because pi is close to 3. And you'll notice, I mean, as we are very familiar with y equals sine of x, we'll notice that the maximum of 1 and the minimum of 0 are one's smaller than the average value and one is larger, right? The maximum is of course bigger than the average, and the minimum is of course smaller than the average. One thing we can think about is, what is the area under this red curve? Okay, so that is something we just found, right? We found that when we did the definite integral, right? That was 1. The area is 1. On the other hand, what is the area under the blue rectangle? Well, under the blue line, right? It makes a rectangle. Well, that's going to be a rectangle whose height is 2 over pi, but whose width is pi over 2. Huh. All right, so that hopefully isn't surprising. We've got, this is from the integral that we calculated just a minute ago. All right, so this is one thing I like to think about here is, if we draw that rectangle whose height is the average value of the function, we can kind of take all the stuff that's too big, like all of this stuff up here, and say, well, this is floating above the average value, so we'll kind of melt this down into some sort of liquid, and let's see, combine red and blue to make purple, and then that's gonna fill in all of this gap right here, right? So this area right here is gonna counterbalance the area over here, so it kind of melts it down into a uniform height. Another thing you might notice is, well, even though we're going from 0 to 1, the average is not 0.5, and I hope it's clear why. if we were to draw a line directly from this point to this point, if I could get it to pop right in the right place, then exactly in the middle here would be the average value. But look at the way our graph goes. Our graph curves up. It's kind of steeper at the beginning, so it rushes to get higher up sooner, and then it starts leveling off. So the idea here is that because of the concavity of the graph, it's going to change where that average value might show up. Okay. Think about this as maybe some test grades, right? You have some low grades, some high grades, but you don't just average the one low grade with the one high grade, right? If you have more high grades than you have low grades, then your average is going to be higher. So this is, again, it's just an average based on an infinite number of y values. All right, and now we're going to ask the question, if k is equal to the average value of the function, should we always be able to find a value between the two endpoints of the interval such that the function equals the average value? So let me clean up this a bit so we can kind of see the original function again. And I'll ask, does it happen here? And it should be a resounding of course. A resounding of course, because this point right here is the point where the function equals the average value. And is that always going to happen? Well, it should happen because of the intermediate value theorem, right, of continuity of the function. This is actually the mean value theorem of integrals. So yes, it does, provided a continuous function. And so we'll often ask what that value is. In this case, it would be kind of a weird number, right? We'd have to set sine of x equal to 2 over pi. So the x value right here would be the arc sine of 2 over pi, which is a funny answer, but it is an answer. And we would use a calculator if we wanted to get a decimal approximation, but that would be the x value that causes us to get the y value equal to the average value of the function.